So to recap, we have these two complex numbers, a plus bi and c plus di, and we want to compute their product. Now our goal is to minimize the number of real number multiplications in order to compute the product of these two complex numbers. We just saw that the naive approach has 4 real number multiplications, a times c, b times d, and bc, and ad. Now what we want to do is we want to try to achieve just 3 real number multiplications in order to compute this product. What we're going to do now is we're going to try to compute this sum, b times c plus a times d, without computing the individual terms, bc and ad. That's going to leave us with a method for computing the product of these two complex numbers with just 3 real number multiplications needed. How are we going to get this term, bc plus ad? Well, notice it kind of looks like a cross terms. So let's write out the correct expression so that these are the cross terms. In order to achieve this, we need to have b on one side and c on the other side. And we need to have a on one side and d on the other side. So one side has b and a, and the other side has c and d. Expand this out. Notice these two terms, bc plus ad, is exactly what we're trying to compute. What about these other two terms, ac and bd? Hey, notice these are exactly the products that we're computing in order to compute the product of these two complex numbers. Let's look back at this expression. We're trying to compute this sum, bc plus ad. So let's solve it for this term. If we solve it for bc plus ad, then we get that that's equal to a plus b quantity times c plus d quantity minus ac minus bd. Here's the key now. In order to compute this product of these two complex numbers, what are the 3 now real number multiplications that we need? Well, one of them is a times c, just like before. The second one that we need is just like before, is b times d. The third term that we want to obtain is bc plus ad. That's right here. How can we obtain it? Well, let's use this expression. Look, a times c we already know. b times d we already know. What's the third thing we need? We need a plus b times c plus d. This is the third real number multiplication that we need. If we compute these 3 terms, ac, bd, and a plus b times c plus d, then from those we can compute these 3 terms, ac, bd, and bc plus ad. So the punchline is if we compute these 3 real number multiplications, a times c, b times d, and a plus b times c plus d, then by just doing some additions and some subtractions, we can obtain the product of these two complex numbers. It turns out we're going to utilize this idea in order to multiply n-bit integers faster than order n squared time. But before we dive back into that problem, I want to make sure that you appreciate the cleverness of this algorithm. It's really quite amazing. I mean, look at what you're computing here. You're taking a plus b times c plus d. Now, one of the complex numbers that you're inputting is a plus bi. So what are you doing? You're taking the real part and the imaginary part, and you're adding those up. And that gives you a new real number, a plus b. Why would you consider looking at this number a plus b or this number c plus d? Why would you consider taking the real and the imaginary part of the same number and adding those up? Somehow by looking at the real plus the imaginary part for both of these complex numbers and multiplying those together, that gives us a way for computing the product of these two complex numbers faster, or at least using fewer multiplications. Just think about it for a specific example. Let's say you're trying to compute 5 plus 3i times 7 minus 6i. What are you using here? You're using 8 times 1. So why would you think to use 8 and 1 from these numbers in order to compute the product of these two complex numbers? It's really quite clever.